nuclear chemistry, radioactivity. And do please make sure to pronounce it nuclear, not nuclear. It's not spelled that way. Homer Simpson may say it that way as he works at his nuclear power plant, but it is definitely not nuclear. Thank you very much. This is the one and only lab that doesn't deal with regular old in-the-lab chemistry dealing with transferring and sharing electrons, doing a chemical reaction. A nuclear reaction was what the alchemists failed to do for hundreds of years. All those guys with their get-rich-quick schemes trying to convert mercury into gold and failing miserably because they were trying to change the identity of an element, and you can't do that by mixing stuff together over a fire, by doing a chemical reaction. Now, thank you to all the alchemists for discovering pretty much the foundation of all of modern chemistry, but if they had hoped to succeed in converting mercury into gold, they would have needed to do a nuclear reaction. And you can do that doing a nuclear reaction. It's just that it would take so much energy and expense, it wouldn't be worth it in the end to get that gold out. That being said, we are going to explore several issues having to deal with radioactivity that you have experienced in your everyday life. For example, have you ever wondered why the X-ray tech leaves the room when you're getting your X-rays? And why the X-ray tech is standing behind a wall that, while you can't tell it by looking at it, is probably lined with lead? Or why the dentist puts that big heavy lead blanket over your body when you get your teeth X-rayed? Or why you don't want to get too many X-rays every year? Well, we'll explore those issues in this lab. So first, what is radioactivity? It is the radiation emitted by radioactive elements. Well, what's a radioactive element? That which are unstable. The nuclei are unstable, not the wrong number of valence electrons, so they're unstable and chemically reactive. These are nuclei that are unstable, and so they are nuclear unstable. They radioactively decay and become different elements. When unstable elements, which are unstable for reasons that aren't fully known, we believe there's some sort of magic number to the number of protons and neutrons and the ratio there between in the nucleus, but it's not fully understood yet. But in any case, we know that there are plenty of unstable nuclei, and when they decay, when they become a different element by changing the number of protons in the nucleus, they can emit three in our textbook, types of radiation. And the first type is an alpha particle. Now, an alpha particle is effectively the same thing as a helium nucleus, meaning it is composed of 2 protons and 2 neutrons. However, an alpha particle is not a helium from which 2 electrons have been removed. It does have the same +2 charge. It can be represented using the same isotopic symbol as a helium nucleus. Sometimes this is written 4/2 helium 2+. To show the charge explicitly. But the most common way, and actually perhaps the best way of representing an alpha particle, is this 4/2 alpha. And the reason you want to represent it this way is by having that preceding superscript representing the mass number and preceding subscript representing the atomic number or number of protons. It's even easier to balance a nuclear equation using these types of symbols than it is to balance a regular chemical equation, at least in my opinion. Because these guys are so heavy compared to the other particles, okay? Compared to, a heavier atom, it's very, very light. But compared to the other radioactive decay particles, an alpha particle is very, very heavy. And therefore it moves slowly because the rule is lighter is faster. Since it is slow moving and highly charged, a +2 charge compared to the other particles, -1 charge or no charge, it interacts strongly with matter chemically. Okay, having that +2 charge, it'll rip electrons off of other things. It will oxidize other things very easily. It's so heavy, it moves slowly, it will, quote, have time to interact chemically with the things that is passing through. And therefore, it has relatively low penetrative power. meaning of the unstable nuclei decay particles, an alpha emitter is the, quote, safest for humans. That being said, you do not want an alpha emitter inside your body. For example, radon is an alpha emitter and kills via lung cancer an estimated 20,000 people in the United States alone every year. Pretty silly for something that you can blow it out of your basement if you have a fan, and you can have a simple radon detector in your basement to make sure you don't have radon in your basement, and the cure for which, if you catch it early enough, is standing on your head. If you have radon in your lungs, it's a very heavy gas. All you have to do is stand on your head and it'll come out. But you have to catch it early enough because it is an alpha emitter and it'll just sit in the bottom of your lungs and effectively blow little holes in your lungs until you get lung cancer. And lung cancer is a very fast-acting cancer. A friend of mine's fiance got lung cancer. He was just walking down the street, thought, whew, I don't feel so good. Went to the hospital. They said, you have lung cancer. And in 3 weeks, he was dead. So it's a quick one. And he was a young guy. He was in his early 30s. A beta emitter is emitting a particle that is effectively the same thing as an electron. However, it's an electron ejected from the nucleus. Say what? There's no electrons in the nucleus? And that's some of the magic of nuclear chemistry. When a neutron becomes a proton in radioactive decay, it ejects an electron because you have to maintain charge even in nuclear reactions. So the symbol of a beta particle is beta 0, no mass number, over -1 atomic number. Weird to have a -1 atomic number. I agree, this is a strange symbol. However, again, using this symbol will make balancing a nuclear equation involving a beta emitter very simple. Because they are lighter and have less charge in terms of magnitude, not because -1 is smaller than +2, -1 absolute value, 1 is less than 2. They have greater penetrating power. Lighter is faster, so the beta particle is moving quicker. It's a smaller charge, so it can get into material before it chemically interacts with it farther. And so you need better protection for a beta emitter. A beta emitter is what is used in this experiment. Now, that being said, as you'll see in the video for the lab, a beta emitter still won't make it through your skin. So you can have a beta emitter in contact with your body for a limited amount of time, relatively safely. But if you put on gloves or put any sort of clothing or a piece of paper between the beta emitter and you, you're likely safe. It just can't get through very much material because it is still pretty chemically reactive. Finally, gamma radiation is a wavelength of light, as you learned in an earlier chapter in the textbook. So it's moving at the speed of light. It is very, very, very highly penetrating, but because it's so high energy, it leaves a trail of ions in its wake, as do beta particles or alpha particles for however far they do travel through a material. So all of these types of radiation are ionizing radiation, which allows us to detect them with a Geiger counter, as you'll see on a later slide. So gamma radiation, you really got to protect yourself. And that's the reason that if you go in for radiation therapy, they're blasting you with gamma rays. With all apologies to the folks at the comic book companies, if Dr. Bruce Banner had blasted himself in the brain with gamma radiation, he would not have turned into the Hulk. He would have turned into dead. Because what gamma rays hit, gamma rays kill. So we can use a Geiger counter to detect any kind of radiation because they are all ionizing. They all leave a trail of ions in their wake as they travel through something, no matter how far into it they may travel. The Geiger counter and other similar types of radiation detectors measure things in counts per minute, or clicks, just how many ions are being detected, how many radioactive decays are being detected per minute. The Geiger counter also will detect natural radiation in addition to any sort of synthetic radiation source that you put in it, and so you have to subtract that out. Okay, a Geiger counter will measure cosmic radiation from space. Most of that is blocked by the environment, by the atmosphere, but maybe a click or two per minute will get through. If you're inside a building and using a Geiger counter, and the building's made out of concrete, concrete contains uranium in small amounts, and uranium radioactively decays certain isotopes, and so you could be detecting that. So you need to subtract out the background radiation from any sort of total radiation count that you get as you do an experiment. So we're going to look at two factors in this lab for what can protect us from radiation. One thing is distance from the source. This is the reason that the X-ray tech goes to the next room, because it's not just that doubling the distance doubles the protection. Doubling the distance squares the protection. If you went 4 times away, it would be 4 squared, 16 times the protection, and so on and so forth. However far away you move, it's an inverse square. The strength of the radiation, R here, is inversely proportional to 1 over, okay, inversely proportional. So it's, or proportional to 1 over d squared. Inversely proportional to d squared. Inversely proportional. Proportional to 1 over is the same thing as being inversely proportional. Got that? R is proportional to 1 over the distance squared, or R is inversely proportional to distance squared. Thus, as distance increases, strength of radiation source rapidly decreases. We'll measure that factor. You can also block radiation with various sources of shielding: skin, paper, plastic, aluminum, lead. It depends on how thick the material is and how dense the material is. So yeah, you could just have a paper gown over yourself at the dentist's office, or you could have a lead gown over yourself at the dentist's office when you get an X-ray. Lead is way, way, way more dense than paper. Any of the radioactive decay particles are going to have a tougher time getting through lead than they would through paper. And if we have thicker paper or thicker lead, it's going to protect us even more. So here's what the Geiger counter, one of the Geiger counters in our lab, looks like. It's just a big box. We have other ones that are just like a wand that we hook up to our old pal, the Vernier interface, the LabQuest interface. But this is the one that's in use in the video, and it has a place to put your radioactive source, and it's got different slots so you can get further and further away from the detector, which is up in here. So you can move your source further and further away and measure the effective distance. It also has slots for all of these different shielding materials. This is just a storage case. You just take one of these shielding materials out and slop it in one of the slots between the radiation source and the detector to measure the effect of different types of shielding material and different thicknesses of different types of shielding materials. Things we got to watch out for. For the distance experiment, you got to make sure that the shielding is constant, and we're just not going to use any shield when we do the distance experiment. When we measure the different types and different thicknesses of shielding, we got to make sure the distance stays constant so that we don't change two things at once. That's a basic tenet of doing experimentation, is you try and keep all of your variables except one constant and measure the effect of changing that one variable. When you start changing multiple things at once, it gets a little hard to keep track of it. So think about what would happen if you move the source closer to the detector or further to the detector as you were changing your shield. And as always, this lab works very, very, very well, but keep in mind that making a mistake is not a valid source of error. Oh, the person must have moved the thing as they changed the shield, even though we didn't see it. You have to say what did happen in your experiment, not what could have happened in your experiment. So congratulations, you have made it through all of the experiments this semester. I hope you enjoyed it and have a great break from school after you pass and ace all of your finals.